The solar shade deploys at the L1 point between Venus and the Sun, the precise gravitational balance where a structure can hold position indefinitely, facing the solar disk, blocking it completely from the planet behind. The deployment is nominal. The alignment is exact. The solar input to Venus drops to zero. On the surface, the instruments confirm the change. The engineers watching the telemetry confirm the change. The surface temperature reads 465 degrees Celsius. The next day, 465 degrees. The next year, 465 degrees. 6 years after deployment, every instrument on every probe still functioning near the surface returns the same number. The shade is working exactly as designed. The solar shade works perfectly, and the planet doesn't cool, because the problem was never the sunlight. That result is not a malfunction. It is not a calibration error. It is the planet responding with complete physical accuracy to an intervention that addressed the wrong variable. The sunlight was the input. The atmosphere was the storage system. Cutting the input does not drain the storage. It only stops adding to it. The planet now holds 92 atmospheres of dense carbon dioxide at 465 degrees Celsius, and the only mechanism available to reduce that temperature is the same mechanism that operates on every planet without an ocean to assist it: infrared radiation from the top of the cloud deck, leaking heat into space 1 photon at a time. That process has a speed limit. Physics sets it. Engineering cannot negotiate with it. Every object above absolute zero emits thermal radiation. The hotter the object, the faster it emits. Venus's cloud tops are hot enough to radiate meaningfully, but the atmosphere below them is so optically dense that infrared generated at the surface struggles to escape without being reabsorbed by the gas layers above it. The energy works its way upward slowly through a column of gas 92 times denser than Earth's entire atmosphere before it reaches a layer transparent enough to let it escape into space. The cooling rate is not fast. It is not medium. Applied to the total thermal energy stored in the Venusian atmosphere, the rate produces a cooling timescale measured in tens of thousands of years under complete solar blockage, and that estimate assumes ideal conditions that do not account for feedback mechanisms that slow the process further as the temperature drops and the emission rate decreases. 10,000 years is longer than every recorded human civilization combined. To understand why that number is not an approximation but a hard physical constraint, the calculation has to be grounded in what the atmosphere actually contains. Venus's atmospheric mass is approximately 93 times Earth's. Earth's atmosphere holds a quantity of thermal energy that researchers can measure and model: the greenhouse effect, the heat stored in the troposphere, the way the ocean and atmosphere exchange energy across seasons. Venus does not have an ocean. It has 93 Earth atmospheres of carbon dioxide, a molecule with significant thermal storage capacity per unit of mass, compressed to 92 bar at the surface and sustaining 465 degrees uniformly across both the day and night sides of the planet. The night side never cools because the thermal mass is so enormous that the 12-hour absence of direct sunlight during a Venusian night, which lasts about 58 Earth days, cannot move the temperature by a measurable amount. The planet's own stored heat is sufficient to maintain near constant surface temperature regardless of solar input on any timescale shorter than geological. That is the condition the solar shade is trying to change. The shade is a real engineering applied to a real problem. The problem is that the shade addresses energy input, and the variable that determines surface temperature at this stage is not input, it is inventory. The Soviet Venera program spent more than 2 decades trying to operate hardware on Venus's surface. Between 1970 and 1985, 10 probes successfully landed and returned data. Venera 13, which landed in March 1982, holds the operational record, 127 minutes before total system failure. It was built with titanium pressure vessels, insulated electronics, and every hardening technique available to the Soviet space program at the time. It was not sent to do anything permanent. It was sent to take photographs and soil measurements and transmit them before dying. It achieved that. 127 minutes. A terraforming project that requires surface equipment to assist atmospheric processing, seeding chemical agents, deploying conversion systems, monitoring atmospheric composition changes, needs that equipment to function not for 2 hours, but for a duration comparable to the cooling timescale itself. Not for years, not for decades, for thousands of years, continuously, in an environment that destroyed the most capable probe humanity had ever built in the time it takes to watch 2 films. The gap between 127 minutes and 10,000 years is not an engineering challenge. It is a ratio of approximately 3 million to 1. No material science roadmap in existence projects a path to hardware that survives Venus surface conditions for 3 million times longer than the current record. The standard acceleration strategy acknowledges the surface equipment problem and proposes to work from above rather than below. Seed the upper atmosphere with engineered microorganisms or chemical agents capable of converting carbon dioxide into solid carbon compounds, reducing the atmospheric mass directly and accelerating the cooling by shrinking the thermal reservoir. The logic is sound as a direction, reduce the inventory rather than waiting for it to radiate. The arithmetic is where it fails. The Venusian atmosphere contains approximately 480,000 billion kilograms of gas. Converting a meaningful fraction of that mass into solid compounds requires driving a chemical reaction at planetary scale continuously across a volume of atmosphere so large that the conversion rate of any biological or chemical agent, even operating at theoretical maximum efficiency, is negligible against the total inventory. Biosphere 2 attempted to maintain a stable closed atmosphere for 8 people in a structure covering just over a hectare of Arizona desert. Oxygen levels dropped to dangerous lows within months. Atmospheric chemistry drifted in ways the models had not predicted. The mass of gas being managed was approximately 10,000 tons. The Venusian atmosphere is larger than that by a factor that makes the comparison meaningless. No analogy from closed ecosystem research scales to planetary atmospheric conversion. The numbers belong to different categories. The shade requires maintenance. That constraint arrives quietly but does not leave. A solar shade at the L1 point is a precision orbital structure. It requires continuous keepsaking to hold its position against the competing gravitational pulls of the Sun and Venus and the pressure of solar wind. It requires attitude control to keep its reflective surface oriented correctly. It requires micrometeorite repair as the interplanetary environment slowly punctures its surface over time. Every mechanical system aboard it has a lifespan. Every electronic component degrades under radiation. The shade must be continuously serviced, partially rebuilt, and eventually replaced, not once, but repeatedly across the entire duration of the cooling project. The civilization maintaining the shade must sustain uninterrupted technical capability and political commitment for a period longer than all recorded human history. No gap is acceptable. A shade that fails for 50 years while a funding crisis or a political collapse interrupts the maintenance program allows Venus to begin receiving full solar input again. The thermal inventory that 50 years of partial cooling had marginally reduced begins climbing back toward equilibrium. The clock resets toward baseline. Every century of progress made before the failure is partially or fully erased, depending on how long the shade was offline and how much the surface temperature had actually moved, which in the early millennia of the project is close to nothing. This is the structure of the dependency that makes Venus terraforming categorically different from other large engineering projects. A dam, a canal, a power grid, these are structures that once built perform their function passively. They degrade and require maintenance, but the function they perform does not reverse the moment maintenance lapses. A solar shade performing planetary cooling reverses thermodynamically the moment it stops working. The progress it accumulates is held only as long as the shade is operational. The project cannot bank its gains. The alternative to waiting for thermal radiation, stripping the atmosphere directly, accelerating mass off the planet rather than waiting for the planet to cool, resolves the timescale problem by replacing it with an energy problem that is larger. Moving the Venusian atmosphere to escape velocity requires accelerating roughly 500 quintillion kilograms of gas to a speed of about 10 kilometers per second. The energy required to do that exceeds the total energy output of human civilization across its entire recorded history by multiple orders of magnitude. There is no power source available, proposed, or theoretically foreseeable that could provide that energy on a useful timescale. Stripping is not a more aggressive version of the cooling plan. It is a separate proposal that fails for a completely different reason under a completely different physical law. Mars presents the comparison that Venus proposals consistently avoid making explicit. Mars has an atmospheric mass less than 1% of Earth's. Its thermal inventory is a fraction of Venus's. Its gravity is low enough that modifying its atmosphere costs less energy per kilogram of material moved. Its surface temperature is cold rather than hot, which means the engineering direction is toward warming rather than cooling, a problem with more available energy sources. Its surface can be reached by hardware built to current specifications. The record for Mars surface operations is not 2 hours, it is measured in years, and the hardware doing it was not built to extraordinary tolerances. Mars is hard, it is not in the same category of hard as Venus. That distinction is not a preference, it is a thermal mass calculation. NASA's Planetary Science Decadal Survey, which sets research priorities for the coming decade of space exploration, does not include Venus surface terraforming as a funded research direction. The Venus missions currently in development, including Da Vinci and Veritas, both approved for development in recent years, are atmospheric probe and surface mapping missions. They are designed to gather data, not to initiate modification. The scientific community studying Venus is learning what the planet is. The engineering community is not building what it would take to change it, because the thermal mass numbers are available to anyone who looks, and those numbers end the conversation before it reaches the budget stage. The solar shade at L1 is still working. The alignment is still exact. The surface instruments are still returning the same number they returned on the first day of the mission, the same number they returned 6 years later, the same number they will return a century from now if the shade holds position and nothing degrades. The planet is cooling at the rate physics permits. That rate will eventually, across geological time, move the temperature. It will do this whether or not anyone is watching. It will do this whether or not the shade survives. It will do this on the timescale that the civilization that built the shade will not live to observe. The thermal energy stored in 92 atmospheres of carbon dioxide does not respond to engineering ambition. It responds to time, more time than the concept of a terraforming project was designed to contain.